So, I want to talk about WebRTC exposed. What we can learn from black box exploration of some popular voice and video services. So, I'm Philipp Hancke, also known as Philipp. I'm one of the top Google contributors to the WebRTC library, and I report a lot of issues. So, as Greg said, I work for Hancke. We're the people behind Talkie.io, which is one of the first WebRTC multi-user services we launched back in February 2013. So we have lots of operational experience, and we've seen most of the bugs since then. So black box exploration of popular voice and video services. Services like WhatsApp, 800 million users, FaceTime, 10% of mobile voice over IP, FaceTime Messenger. So what does black box exploration mean even? Well, generally it's observing system behavior without any access to the internals. So you poke the system, see how it responds to your actions, and learn from that. It means no access to the source code, no access to any design documents, and most importantly, no cooperation by the operator is required. So I didn't have to sign an NDA with WhatsApp to look at their service, and I can talk about it in public. But the interpretation of the data is very difficult, because when doing network dumps, it's lots of small packets, and it requires lots of experience. So black box exploration and WebRTC, what does that mean specifically? Well, if you go to WebRTChacks.com, you find a lot of technical content on WebRTC. And back in March 2014, Chad Hart and some others did an analysis of the Amazon MAYDAY service. It was called Amazon MAYDAY Trace, and at that time it was very important because it proved a significant WebRTC deployment. And they were using Wireshark, which is the network engineer's favorite tool for that, and showed that Amazon used the Google WebRTC library and some Oracle session border controllers. So the next step was an analysis of Hangouts I did back in August 2014. That was shortly after Google launched the WebRTC-enabled version of Hangouts. And it was pretty important because it showed how Google wants to use WebRTC. Before that, we only had the AppRTC sample. That didn't tell us much about multi-user, because it's just one-on-one. And it was using the great WebRTC internals page in Chrome, which allows you to see all the API calls that are used by a web page. So the next thing I did was something called Hello Decode. So if you know Mozilla's Hello, it's a one-to-one video chat built into Firefox. It's a small button which is rolled out to every Firefox user on the world. And it showed us how Mozilla intends to use WebRTC. And again, it's using WebRTC internals in Chrome to do the analysis and a man-in-the-middle proxy. Because TalkBox, which powers Hello, did some tricks with the signaling protocol, which made it not so easy to decode their WebSocket traffic. So shortly afterwards, I got a mysterious email on my personal account, not my Hancke account. So the subject was question. You've done great teardowns of MAYDAY, Hangouts, Hello. Could we hire you to look at some more applications? Okay, sounds somewhat suspicious. So that email was from Serge Lachapelle. He's Google's WebRTC Director of Product Management, one of the leaders and founders of the WebRTC project at Google. And he's a really great guy. And we came to the conclusion that it would be best if I did that in fully public. So we're looking at a number of popular services, and why are we doing that even? Well, most importantly, shows the adoption of WebRTC, which was very important back in the days of Amazon MAYDAY. Also, we want to understand how people use the WebRTC org library, which is the BSD licensed library Google provides, which powers Chrome and which powers a lot of the mobile services that people have. Like our Talkie iOS app is powered by it, the Appearing applications for iOS and I think Android as well, and numerous others. So, even more importantly, we want to encourage feedback because often people take the library, say they make tweaks to it, enhance it, make it better suited to mobile, and then don't contribute back, which is pretty sad. So, one thing we saw in late 2014 and early 2015 is a shift to mobile, which is quite interesting because originally, back in 2012, we thought WebRTC, it's bringing voice and video to the open web platform, but we're seeing more adoption on mobile. And last but not least, we want to identify some best practices and maybe learn some new tricks. So, Hangouts and Hello were spare time projects for me. This is a full-time project I'm working on. So it's 2 weeks full-time for WhatsApp, 2 weeks for Messenger, and another 2 weeks for FaceTime. So let's look at some of the tools I used to do that. In the browser, it's pretty easy. If you have a service that is using the browser, it takes about 5 minutes to decompose it, if you're me. So the most important tool here is Chrome's WebRTC internals page, which is the WebRTC engineer's favorite tool. It shows you all the API calls, all the statistics you get from the library, and you can break down things very easily with that. In the browser, you also have the network console to take a look at all the signaling traffic, which gives you information about whether TRICKLE ICE is used, how the SDP is manipulated, if at all, and stuff like that. And if that doesn't work, you still have Wireshark, which is a packet capturing tool. It's the voice over IP engineer's favorite tool. And you can create network dumps with it. So mobile, which I looked at, is a little more tricky because you don't have such great debug opportunities. So I used a little router called the Wi-Fi Pineapple to make those network dumps from the mobile devices. It's really the wireless hacker's favorite tool because it offers a lot of wireless hacking tools out of the box, even though I just used a simple TCP dump. So on the mobile, capturing the signaling traffic is very difficult. You need a man-in-the-middle attack on a routed device to look at the signaling channel. I haven't really used that yet, but maybe at some point in the future I might. So, popular services. WhatsApp, 800 million users. Facebook Messenger powers 10% of mobile voice over IP according to Mark Zuckerberg. And Apple's FaceTime, which is huge on the iOS devices, but it only works on iOS. And there are many more to come. So it's a series of blog posts with a focus on mobile services. We're talking about 25 services analysis. So WhatsApp is doing voice calls. They rolled it out in the end of March for Android and a little later on iOS. It's not using WebRTC. Instead, it's using an old library called PJZip, which is rather old-fashioned. It's a couple of years old. It's quite reliable. But unlike WebRTC, it doesn't use the interactive connectivity establishment protocol for breaking through nets. It's using the somewhat older stun mechanisms, and it is using the old security description for encryption, which is an old mechanism that came up a decade ago and which should not be used in WebRTC. So it might use WebRTC echo cancellation, even though the echo cancellation is really horrible there. and some other components. But if they do that, they're probably violating the license because it's a BSD licensed library, so you need to acknowledge that you're using it. And they're not doing that. Well, the audio codecs they use remained a complete mystery. We had some people from Google looking at it who built the ISAC codec, and they don't know what it is either. It is not Opus, and it's looking completely different from everything we saw elsewhere. And the important thing we found is that the call is always relayed via a relay server for the first few seconds. Actually, in the source code, they have strings indicating that they call this a conference bridge, which is quite interesting because it means they might roll out multi-party support at some point. So, and if possible, if they can establish a peer-to-peer connection between two clients, then they switch to that connection to take the load of the relay servers. And that potentially decreases the call setup time, which makes the UX better. So, FaceTime. Well, it's not using WebRTC. It's not a surprise. It's pretty old now, and it's from Apple. And Apple doesn't comment on WebRTC. But they have years of deployment experience, and it's rumored to be really big, the order of several 100 million of calls per month. So they've probably tuned it a lot. And I have to admit, the quality is really impressive. It's an integrated experience between hardware and software. And WebRTC still has to get there. So it's using the H.264 and H.265 codecs for video. They licensed the AAC ELD audio codec from Fraunhofer. And again, they're using security descriptions for encryption. And one of the nice things I found is that they negotiate image size to send an optimal resolution. So if you have an iPad calling an iPhone, it doesn't make sense for the iPad to send full resolution to the iPhone. And that is one of the nice UX tricks we learned from that. So it turned out they're using H.264, not H.265, even though H.265 is rumored to be the better, the more modern codec. But it costs them more CPU power, and that means more battery life. And if they have enough bandwidth, the advantage of using H.265 goes away. So we still need to repeat that analysis using a GSM microcell probably to see H.265 used. It is a somewhat archaic architecture. It's a combination of XMPP and ZIP, which probably dates back to the good old days of iChat AV. And they say in their documentation, please unlock port 16402, like it's 1999. WebRTC can do better. And it uses turn servers. So turn is the protocol used for relaying in WebRTC as well. And again, it's using the turn servers first. And as we've seen with WhatsApp before, this makes the call setup slightly faster. And they also use a very fast mechanism to do the candidate allocation on turn. So you need to get your relayed IP address from the turn server, and they don't require any round trips for that. Whereas Chrome currently requires 2 round trips between the client and the turn server for that. And that, again, contributes to the call setup latency. And doing that is currently not possible with the WebRTC API. But now that we know about it, we can fix that. So, Facebook Messenger. It does audio calls. Mark Zuckerberg said 10% of mobile voice over IP is using that. And they recently, like last month, launched video calls. So, it works on Android, it works on iOS, Chrome, Opera, and Firefox. So, no surprise, it's using WebRTC in the browser. And on the mobile apps, they're also powered by the WebRTC library. And unlike WhatsApp, they even say that in their third-party license details. So they really show how to do it nicely. even though they're not yet contributing back. So the browser usage, when you look at that in Chrome's WebRTC internal page, it looks pretty standard. I looked at it in January and thought, OK, not much interesting here. Let's do something more interesting. However, if you look at what the mobile apps do, that is going to be really exciting because it's heavily tuned and Facebook really has learned the mobile-first lesson. Mostly because most of their traffic is probably going through two mobile devices. So they're using an old relay mechanism in the Google library, which provides a slightly faster call setup, even though it's probably not as secure as Turn. And they tweaked some codec parameters. So you can tweak the packetization and the frame size to yield larger packets, which might work better on some wireless networks. And more importantly, they use different audio codecs. So if you have two Android devices, they are using a variant of ISAC called ISAC Low Complexity. If you've never heard of that, few people outside of Google did probably. Between an Android or iOS device and Chrome, the ISAC codec is used because it's lower complexity than Opus. And if they're talking to Firefox, they fall back to the Opus codec. And even there, they have tuned it to reduce the complexity because Opus is pretty computationally expensive on mobile devices. So they tuned it for mono usage because mobile phones typically only have a single microphone and speaker. So stereo doesn't make sense. And they use the standard DTLS encryption when talking to the browsers. Because 2 years ago at the IETF, we decided that WebRTC browsers must not use the STS mechanism. That was shortly after Snowden, and we preferred the stronger encryption provided by DTLS. So the thing is, they use the old STS mechanism between two applications. And that is somewhat bad. And the reason they probably do that is that it reduces the startup time. So no round trips required for this. However, unlike DTLS, security descriptions don't provide perfect forward secrecy. So perfect forward secrecy means you can't decrypt the call after it happened if you obtain the keys. So security descriptions enables retroactive decryption, which at some point is going to be a legal liability for Facebook. And of course, it makes the NSA happy if they can get encryption keys for 10% of mobile voice over IP traffic. Sure. So there is a common theme here, which is described by Chris Cranky in an old blog post. It's called the need for speed. And it's the call setup time, because that really has a huge impact on the UX. If you have to wait several seconds before the person you're calling is answering, you're going to feel that a lot. And this call setup time is influenced by two things. It's the interactive connectivity establishment and DTLS, mostly. So what we do here is using relay servers, which we always considered as a fallback for the traffic because we don't want traffic to go over them because it's expensive, even with Twilio. So we always considered them a fallback. And what we're seeing here instead is that we're going for the relays first for usability reasons. And it's possible to do that in Chrome as well today. And you can make the switch from the relay servers to the peer-to-peer connection unnoticeable. So the UX is already good. But it requires an ICE restart, and if you're a web developer, you don't care what that is, and you don't want to do it. So the thing is, turn is the thing that is most likely to work. If you remember the failure during the keynote yesterday, that might have prevented it. So, and in the future, the most likely to work candidates should be tried first, not the highest priority, which is actually the title of one of the recently filed issues in the Google WebRTC library. So they're listening to this feedback, and they're creating issues and then fixing them with high priority. So another thing that creates latency here is this allocation of relay candidates, which takes time. 2 round-trip times currently, and Apple just showed a 0 round-trip time mechanism. And we're discussing how to solve that in WebRTC in a way that is secure. So last but not least, DTLS versus STS. Well, that's my only comment on that, mostly. So DTLS has some issues with startup time when there is packet loss. But the important thing is it provides forward secrecy. And that is something we really want to have. And what we're likely going to do is to optimize DTLS a little for the case of packet loss, things like fragmentation and robustness on mobile networks. And the good thing is, if we combine this DTLS stuff with the relay-first approach, then we have a way to hide this latency from the user. So we can establish a connection before the call is accepted even. That's a known technique. It's called early transport warm-up. However, there's a privacy concern. It exposes the IP addresses of users. So if someone you don't know calls you, you don't want them to know your IP address. You want to have an explicit consent to expose your IP address to them, like accepting the call. So if we combine that with the relay-first mechanism, then we're exposing the IP addresses of turn servers. Well, who cares about that? They run in the cloud somewhere, and it's not the IP addresses of users. And then we can switch to peer-to-peer after the user accepts the call. So if you want to talk to someone, then you have to give them your IP address. That's mostly unavoidable. And that way the ring latency, so the time until the user takes the phone from the pocket, decides whether to accept the call, and then accepts the call, hides any latency introduced by DTLS. So we're pretty confident that we can solve that problem like that. So again, why are we doing all this? It's a lot of effort. Because in the end, it's the user experience that matters. So we've seen that before. Forwarding ports like it's 1999, no longer. Instead, we have the ICE mechanism, which does all that for us. And we have been optimizing that with something called TRICKLE ICE. So you send any candidates you need to exchange as you gather them. Instead of gathering them all, then sending a big batch of candidates. This has been made common in WebRTC, and it has a huge impact on the call setup time. So without TRICKLE ICE, it takes like 10 seconds to establish a call, and with TRICKLE ICE, only the worst case scenario takes 10 seconds. Well, most of the time, it's in the order of less than a second. Google has tuned the WebRTC sample to go to 500 milliseconds on average, which is pretty awesome. And what we see in Chrome, and this is a quote from the Chrome release notes, at the risk of sounding like a broken record, Chrome 43 continues on the line of performance and stability. So the Chrome team really cares about the user experience, and they're putting a lot of effort into that. And this has been in the last 2 or 3 Chrome releases. So we see this need for speed. And it's because the UX matters. And sometimes the order of those small packets matters, even if the user will never understand why. And that's it. Thank you very much.